All right, let's open up to page 197. We're going to continue talking about inverses today, specifically in terms of derivatives, but we're going to take a look at inverse trig derivatives. These are going to be our last derivative shortcut rules. So after today, we're not going to have any other rules, shortcuts, processes to be familiar with or to know. So this is it. Okay, and it's not going to take us that long because we're just going to go over the shortcuts themselves, do a few examples, and then I'll let you try some of the homework problems for practice. I mean, we can do them together if you really want to. But by the end of the period, I'll let you know who your partners are for tomorrow's quiz. Okay? And just a reminder, test is next week. So from last year with our study of trig, we should be familiar with these 6 different graphs. Sine and cosine are kind of the more recognizable ones because they're the waves. And then tangent was that weird kind of S-shaped graph that repeated itself, and we had those asymptotes going on. Then you have the reciprocal graphs where secant and cosecant were those parabola shapes that had the asymptotes. And then the cotangent graph was just basically the flip of the tangent graph, okay, with those asymptotes. So I'm hoping we recognize at least these 6 different shapes. What we're going to try to do is discuss the inverse graphs because we know how we can switch the x's and the y's, and then we'll go over some derivatives or shortcuts for the graphs. So one thing that we need to be familiar with are 2 different ways that an inverse trig function could be written. You could have arc sine of x, where they actually say arc or arc out front, but they also might write it as sine inverse of x. So whenever you come across one or the other of these, they mean the same thing. Okay, it just depends on what notation or wording they want to use. So I'm hoping when we look at these graphs, it kind of makes sense. If you were to take this wave shape and switch the x's and y's and kind of plot those points, can you think about what the inverse graph might look like? If this is a wave that's going left and right, what do you think the inverse would look like? A wave that goes up and down. Okay, now the issue with that is if this wave goes up and down, is that a function? No. So in order for us to be certain that if we plug in one thing, we get out one thing, we actually chop off certain portions of this wave. And that's where this section comes from. So on the regular sine graph, we're really only finding the inverse of this little piece, because anything after that would not be a function. Okay, it would not pass the vertical line test. The same thing is kind of happening with cosine. If it's a wave that goes left and right, you would have a wave that goes up and down, but again, that's not a function. So for the inverse cosine graph, we only take a look at a certain chunk of it, and that's this portion. What about the tangent graph? If we have the S shape that goes up and down, the inverse would be left and right. Okay, now if it's an S shape that kind of repeats itself, it would look something like this. But again, notice how that's not a function. So we're only dealing with one of those. That's where this inverse tangent graph comes from. And that's just the middle section. All right, same thing kind of going on with cotangent. Instead of a wave going up and down, they're now going left and right. So we're just doing this section. Okay. What about the secant and cosecant graphs? Instead of having parabolas that open up or open down, kind of a square root graph. They're going to open left and open right. Okay? But notice how, again, that's not a function. So we chop off a certain section of it. So for this cosecant graph, which happens to be this bottom right-handed one, notice how we have that asymptote at 0. So we're keeping this asymptote, and we're just using half of the parabola on either side of that asymptote. And then the same thing's going on with secant. Notice how the parabola or the asymptote is positive. It's above the x-axis. So it looks like we're using this asymptote because it's a positive x value, and then we'll have half the parabola on either side. Okay? So the inverse trig graphs are definitely related to the original ones. It's just the kind of flipped or switched idea with the whole x's and y's switching. We don't necessarily have to be familiar with these graphs. I just wanted to show you where they came from. But what we're going to do is talk about derivative shortcuts for these graphs. So these shortcuts are basically representing if you were to pick a point anywhere on these inverse graphs, you should be able to find the slope at that point because we have the derivative shortcuts. And what can be tricky, because we're going to take a look at two different examples here, it depends whether we have something other than x on the inside of our function. For instance, what if we have sine inverse of x, or what if we have sine inverse of x squared plus 1? Okay, this one's pretty simple. This one's a little bit more complicated. So we're going to have very similar shortcut rules. It's just that this shortcut rule might be a little different from this one because this one's more complicated. So the first thing we're going to take a look at is just the basic derivative shortcuts for inverses. So what I mean by basic is that it's just an x inside those parentheses, inside the argument. Now, I know there's 6 of them that we're going to go over, but these are the main 2 that are really ever used on the AP exam, if they even put one of these questions on there. So I'm not going to really hold you accountable for all 6 of them, okay, mostly just these 2, but I will tell you if you do decide to go into Calc 2, we discuss the other 4 a little bit more, okay? So we definitely got to know the inverse sine and the inverse tangent. You're going to start to see a pattern, though, after we go through some of these that might help you remember them. So they can be a little bit different. We're just going to write them down and kind of talk about them to see if we can find a pattern to help us out. So the derivative shortcut for inverse sine is 1 over 1 minus x squared. Okay, we have to be familiar with that one. The shortcut for inverse tangent is 1 over 1 plus x squared. Okay, I'll put those in red because those are the ones we definitely have to know. And then secant is a little bit more involved. We have 1 over the absolute value of x times the square root of x squared minus 1. Okay, so we definitely have to remember sine and tangent. Okay, secant is a little different. Can we find any patterns in here to kind of help us remember or distinguish them between each other? Do you see how they're kind of similar, though? Which can either make it easy or make it hard, depending on how you want to look at it. I mean, if they're really simple, it might, or if they're very close related to each other, it might be difficult to distinguish between the two, or between the 3 of them, because they're slightly different. Or you can take a look at it as they're very similar to each other, so it should be easy to remember all of them, because they're not drastically different. It all depends on how you want to view it. Now, let me ask you this. If we can use these as the shortcuts for inverse sine, inverse secant, inverse tangent, what do you think the C derivatives are going to look like? Can we use a previous pattern that we may have seen before with trig functions? They're negative. So cosine would be negative 1 over square root of minus x squared. Cosecant inverse, negative 1 over absolute value of x, square root of x squared minus 1. And cotangent, negative 1 over 1 plus x squared. So if you really take a look at it, there's really only 3 that we have to be familiar with. Okay, these 3 on the left-hand side, because the c derivatives would be the same but negative. So it looks like a lot because there's 6, but again, they're very much related to each other, so you can probably use that to your advantage. Now, this is what the derivative shortcuts are if it's just x. Okay, nothing other than x. What we can do, though, is think about how we can still provide a shortcut if we have some type of function. Now, I know it's x on your paper. I tried to write in there f of x, for instance, sine inverse of f of x. Okay, if we have some type of function on the inside, not just x. So this is where it's going to look very similar to the chain rule that we had, or that e to a power. Remember when we did e to a power, the derivative was e to the power times the derivative of the power? This is going to look very similar. So the normal shortcut for the inverse sine is 1 over the square root, and it's typically 1 minus x squared, but this x is simply representing what was on the inside of the inverse trig function. So if we use the same logic here, we'll have 1 minus f of x squared. Okay, whatever's on the inside, we're just going to square it. And since the inside is a function, something other than x, we're going to multiply by the derivative of the inside. Just like we do for chain rule, just like we do for the e to the power. All right, so the other 5 are going to follow the same suit. For inverse secant, we'll have 1 over the absolute value of f of x, whatever's on the inside, times the square root of f of x squared minus 1. And then times the derivative of the inside. For tangent, we'll have 1 over 1 plus f of x squared, and then times the derivative of the inside. Okay. The c derivatives are going to be the same thing, but negative. So you can write them in if you want to. I'll just do negative 1, and I'll write same down, okay, if you want to save space. Okay, so we're just going to practice these shortcuts today. Again, we really only have to be familiar with inverse sine and inverse tangent, but I just wanted to go over the other ones as well, just in case you were curious. Okay, let's go ahead and check out some on the back. So you may have to flip back and forth to view the shortcut, but we'll see how we can tackle these. Okay, so if you take a look at the first one, it's inverse sine, and the inside or the argument is something other than a simple x. Okay, we have a 3 in there as well. So we're going to use our derivative shortcut for inverse sine. If you have to look, that's okay. What do we think? Inverse sine is
1 over the square root of 1 minus x squared.
okay, so if it was
3x.
okay, minus 3x squared. Yep. And then we got to multiply by the derivative of the inside, which would just be 3. Okay, so this is what our initial shortcut is going to lead us to. Maybe we can clean it up a bit. So this times 3 is actually going to move to the top of the fraction, and that's going to happen all the time. Like if you take a fraction times something, it can move to the top. And in the bottom, we'll have the square root of 1 minus 9x squared, if you actually wanted to calculate that out. So here is our derivative for this inverse sine function. Okay, it's not too complicated. We just have to be familiar with the shortcut, and that's going to help us. What about inverse tangent? 1 over the inside is something other than x. 2x squared, and we're going to square that. Okay, so 1 over 1 plus the inside squared times the derivative of the inside, since it was something other than x, so it'd be 4x. Okay, and if we clean it up, the 4x can move to the top, and we can simplify the bottom. 2x squared squared would be 4x to the 4th. All right, we cannot simplify 4x over 4x because we're adding something else. Just be leery of that. So that has to stay. All right. What about secant? Inverse. 1 over the absolute value. Okay, so we have 1 over the absolute value of the inside times the square root of the inside squared minus 1. And then we got to multiply by the derivative of the inside, which would be 30x to the 5th. So we'll have 30x to the 5th over that denominator. Maybe we'll simplify the inside. 5x to the 6th squared, 25x to the 12th. Okay, power to a power, we're going to multiply. The question is, can we simplify it any more? What do you think, Anuj?
The absolute value of 5x to the 6th will always be positive.
Okay.
So there's no need to put the absolute value there. So then can we factoring it, maybe?
Do you put 6 on top?
Okay, so we can definitely simplify. So there's two different ways you can look at this. Since this is an even power, you know this will always be positive. So if you want to take away those bars, you can, because they're basically insignificant. Okay, we'll take a look at a case where they do matter. Okay, so if that's the case, we can do 30 divided by 5, which would be 6, and then x to the 5th over x to the 6th, we'd have an x left on the bottom. Oh, if you could see that, that'd be good, better. All right, let's do a different one as an example. So let's say we had 30, let's see, x to the 5th. You want to do the second? So then this would be 5x. I've got to think backwards here. I don't know. We'll do this one just as, this would be third. I don't know if this will ever happen, but let's just think about it anyway. What if this was 3 and this was 5? Okay, I don't think that would ever happen because shouldn't this be the derivative of what's in here? Yeah, so if this is a 3, this should be a 4, right? Okay, again, I'm not sure if this will ever happen, but let's just talk about it just in case. So if we were to simplify this one, just as an example, We can clearly do 30 divided by 5 because this 5 will always be positive. So we can definitely do a 6. The question is, what about the x's? Can we simply write x squared inside absolute values on the bottom?
No,
Why not?
because it's an odd power.
It's an odd power. So this has the capability or the possibility of being negative. Okay, if you were to plug in a negative, it would be negative. And by simplifying it this way, notice how it no longer has that ability because the absolute value and possibly the power of 2 would make it always be positive. So if we were to simplify this, you could technically take 2 x's out. So you'd leave 1 x in the top, and then you would have an x to the 3rd on the bottom. Because notice how it still has the possibility of being negative up top. Okay, and the rest can be the same. But we have to be a little leery on when we can simplify x's and when we can't, especially with absolute values. Again, like I said, I'm not sure if this will ever happen because if this is supposed to be the derivative of this, they'll never both be odd, but maybe something worth noting. Okay? All right, those I think went pretty well. Let's try one that's a little bit more involved. So if you were to read this out loud, can you think about some shortcut we can use? Product, right, because you're multiplying 2 functions together. We have 3x to the 4th times the inverse cosine. Okay, so let's go through 1d2 plus 2d1. So our first function is 3x to the 4th, and then we have to multiply by the derivative of cosine inverse. Okay, now cosine inverse should be the same as sine inverse except negative. Okay, so instead of being 1 over something, it should be negative 1 over that something. So we'll have the square root of 1 minus the inside squared. And finish off that derivative by multiplying by the derivative of the inside, which would be 2. Okay, so we have 1 d2. We now have to add 2 times d1. So the derivative of 3x to the 4th. 12x cubed. All right. So let's clean it up. If we look at the 1d2 part, everything before the plus sign, the 3x to the 4th can be moved up top of the fraction, and same with the 2. So we'll have negative 6x to the 4th. And if we want to simplify the bottom, we'll have 1 minus 4x squared. And then we got to add the second term, and they're both being multiplied together, so order really doesn't matter. Technically, we put the polynomial out front, just like you saw in the original problem. So I would say this is more likely to be written as 12x cubed cosine inverse of 2x. All right, and we'll leave it like that. Okay. So these inverse trig functions, like I said, are the last shortcuts that we're going to work with, and we really just have to be familiar with the inverse sine and the inverse tangent. The other ones are nice to know, especially if you want to go on to Calc 2, but for right now, we'll just work with those. Okay. Do you guys have available to you this shortcut list that we did a few days ago? I told you to write it down on a different page. Do you have it? Can we get it out or find it? If you don't, maybe you want to write them down again.
We use this on test.
No. This is a good study tool.
What was the short?
Okay, we already covered the power rule through the original 6 trig derivative shortcuts. We're now going to add on what we've done up to that, or up to this point. So we're going to go ahead and add in the chain rule. We're going to talk about the natural log and the exponential derivative shortcuts. And now we can throw in the inverse sine and inverse tangent. So chain rule is normally where we have an outside function and an inside function. How can we find the derivative of those types of equations? How's our chain rule operate? Go to Nuj.
F prime of g of x
Yep.
times g prime.
G prime, the derivative of the outside, okay, F prime, keep the inside, g of x, times the derivative of the inside, which would be g prime. Okay, so there's our chain rule. Now, these other shortcuts are like the trig ones where we just have to know them. It's not necessarily a process like the product rule, quotient rule, chain rule is. These are just nice shortcuts to know. So we can talk about if it's a basic natural log or if it's a natural log of a function. Same with the exponentials and same with the trigs. So what if it's a basic natural log? Remember that derivative shortcut? If you know the function one, you can actually apply it to this one as well. Maybe you want to look back. I think it was 3.4 that we did that. 1 over x. Good, that's the basic one. What if it's the natural log of a function? You would think, I like the f of x part. How is 1 related to x? It's the derivative of it, right? The derivative of x is 1. So the derivative of f of x would be f prime, okay? So for natural logs, it's always the derivative of the inside over the inside. All right, what about the exponentials? The derivative of e to the x? E to the x. What about the derivative of e to a function, something other than x? E to the f of x times f prime, okay? The basic one is actually the same concept. You'd have e to the x times the derivative of x, which is just 1. So times 1 really doesn't mean anything. That's why we don't write it, okay? So what about these new ones? Inverse sine, the basic one? 1 over square root minus x squared. Good. All right, that's if it's just x. What if it's a function on the inside? Squared, yep. Look at you go, yep. All right, tangent. One over 1 plus x squared. All right, what if it's something other than x on the inside? Yep. Times f prime of x. Good. All right, we're officially done with all of our derivative shortcuts. Okay, so every shortcut we've talked about should be on that page that you were just writing on. Okay, good study tool for you to have. In the meantime, because we have about 15 or 12 minutes left, whatever the case is, if you take a look at some of the homework questions on page 200, those are just examples of these inverse trig ones that we were talking about. So I would suggest trying some of those today, okay, getting used to these new shortcuts. They do involve all 6 of them, but again, sine and tangent, the inverse ones are the main ones that we have to know. Okay, give me a second to bring up your groups or partners, and I'll let you know who you're working with in a little bit.
Can I go to the restroom?
Mm-hmm.
Yeah.
Remember when you told me about that? That I didn't believe it? Wait, I've been like 10 times.